electrolyzer as well as fuel cell. So, these are the content probably I am gonna talk about. So, initially just little bit background, and then why actually we need DC-DC converter. I think you already know about that. And then what are the different types, both non-isolated and isolated, and then I will finish showing some comparison among different topologies. Although I mean we are not gonna go like very detailed, because if you want to go like very detailed, including like operation and then modeling equivalent circuit, both like when the switch is turned on, when the switch is turned off, then I think it's gonna take I mean maybe a few days to finish it. But I believe all of have some background about like different types of topology. So, again I mean most of the existing topology, I mean that actually can be utilized, but having said that, people are still I mean trying to develop new technology for many other application, including green hydrogen as well. So, I already gave that sort of introduction that for like power to hydrogen facilities like electrolyte, as we already mentioned that the capacity is megawatt level, right, and we are also planning to go for like the gigawatt. So, we need very high power, high current DC to DC converter that can be connected maybe in medium low voltage grid, and to do that now focus more on like the high power application. I am not saying that people not are I mean doing research on low power DC-DC converter, because that also has got many other application, but for power to hydrogen application actually we need high power high current converter. Now, as we talked many times that we have like the DC bus, like other one it can be like renewable energy, can be either directly connected or connected through rectifier. Sorry, but everything can be connected to the DC bus, but for either electrolyzer or fuel cell. So, as I mentioned that for electrolyzer input is input DC voltage, right, but in many cases like when you are converting AC to DC or direct DC, you might not get exactly whatever input voltage you need for the electrolyzer, because electrolyzer need lower input voltage. So, you need a maybe buck converter to convert higher DC to lower DC values. And then in the fuel cell, whatever voltage it produced, sorry, I mean here is the arrow should be in like the different direction, not in this direction. So, this is giving like the output fuel cell, but that output voltage might not match with the DC bus. So, we need maybe the boost converter. So, what I am trying to say that in both cases, either electrolyzer or fuel cell, we need actually DC to DC converter. It might be buck or boost, or there are so many other topology as well, but we need a DC to DC converter for both applications. And also when we are integrating with other sources, in that case also we need DC to DC converter. There are multiple role of DC to DC converter. For example, match the output of renewable energy sources, variable which has got variable voltage to meet the specific requirement from electrolyzer, provide constant or control voltage or current for optimal electrolyzer operation. And also we already talked about that, providing MPPT service. And in some cases, if you have got isolated DC to DC converter, then it can also provide electrical isolation, and that is quite important for safety and protection for equipment as well as sometimes for the operator as well. And it can provide better integration with the DC microgrid or even like hybrid energy storage system. So there are a number of functions that you can get from like a DC to DC converter. Now, when you're gonna identify which converter you're gonna use, there are some specifications that you will always be looking for. So your requirement might be that I want very high efficiency, minimum EMI, electromagnetic interference, very high power density that will make the system compact. Definitely, as usual, for all product, we always want like low price, high conversion ratio, like either step up or step down. And when you have got power electronics, in many cases we have got the problem like the ripple in the output current. So definitely we require minimum or even no ripple in the current that will give longer lifetime for both like electrolyzer or fuel cell whatever and other components. So we need pure sine wave, pure DC, not any ripple in the DC, and then fault tolerant capability like other technology like wind farm, when there is a problem in the grid. So these are the function you will be looking for, and this can be achieved through both different types of topology and also better control and optimization. It's not only topology can provide all of them, but also you need the control, in some cases optimization, and then you overall the DC-DC converter can provide or can meet all those requirement. So as I mentioned, like in terms of like isolation, you can convert either non-isolated DC to DC converter or isolated DC to DC converter that can provide like galvanic isolation between source and electrolyzer to provide like safety in large scale system. Now I'm just showing few, but there are so many actually non-isolated converter, but I'm not going to explain all of them. I'm just showing this 5 topology, but also on top of that there are like bidirectional and other topology available as well, and people are still working for many other new technology, and also new switching device, which again I'm going to show some future research direction here as well, but people is still working for new technology as well. And again whatever technology, that's again we want like simplicity, simple control, cost effective, compactness. That's always we'll keep in mind whatever converter technology we're gonna utilize. So again you might be already familiarized with this one, that the traditional buck and boost converter that has been in the market and has been widely utilized in many other application. So that topology also can be used for here the green hydrogen system as well. So this one, the first one is step down. As usual, if you just developed that when this switch is on, what would be the equivalent circuit, and when the switch is off, then what will be the equivalent circuit. So, when the switch is on, definitely it would be like reverse bias. When the switch off, it will be like a forward bias. So, if you just have this two equivalent circuit and do some calculation, you will get that equation for duty cycle is not, and also the ripple in the current, whatever the current is coming in the load, what the ripple, and also the ripple in the voltage as well. So, we always have requirement like what sort of maximum ripple you might be permitted. Based on that, I mean using this equation, I mean we can find the value of inductor and capacitor that might fulfill your requirement. But for this technology, it's like as I say, like it's already widely available. Is quite simple circuit, and cost is comparatively lower cost as well. But again, I mean in terms of step up and step down, I mean there is a limit, because that here what the output voltage, it would be input multiplied by the duty cycle, and the duty cycle like value. So, stepping down definitely less than 1. So, its output would be less than that, but there is a limit. And same for if you go for boost converter also, I mean there is a limit actually you can boost. So, switching device, that people are using IGBT, MOSFET, but there are new switching technologies coming as well. And the inductor function, like that it store energy and it smooth current, and as I mentioned the capacitor that actually reduces the voltage ripple. The diode again just that providing current path when the switch is off, as I already mentioned. We did not show the controller because the next lecture would be control, but that controller here you can regulate the duty cycle based on feedback that you can get from the output, and you design the control, and then you providing like instruction that I mean for the switching. So, that is how I mean you can control as well. So, the same one, I mean if you want to use like with photovoltaic system and fuel cell in between the DC to DC converter, that would be your like a circuit diagram. So, the power is flowing from like PV to fuel cell, I mean to produce hydrogen. And here like some application, power conditioning for electrolyzer, voltage regulation between solar PV and electrolyzer, as I mentioned in between, I mean you can actually control that voltage step up or step down. We already mentioned you could also have like interfacing energy storage system as well, which also can be utilized by using bidirectional DC to DC converter as well. But if you use this sort of topology, you see that when the switch is off, there might be like a discontinuous input current, right, because the power switch is connected in series with the source. And also other problem might be that like at this point, like sometime due to the parasitic inductance, you might get the over voltage in the common, like where inductor, diode and MOSFET are connected, and sometimes that can propagate in the load and sometime in the source as well. So, and also like the conduction losses, or sometime for the diode the reverse recovery voltage. In for that problem people also thinking to use MOSFET instead of the diode, that might be reducing the losses. So, the limitation Again, in many cases, in most cases, that the main limitation coming from that there is a current in the ripple current coming from the that conventional converter, and even if you do experiment, actually you will see that there is actually ripple, although we are using inductor capacitor, but still there are some ripples. Sometimes you can reduce the problem, as I say, I mentioned that by selecting the correct inductor value or by having the optimal switching frequency of the switch. But again, if you increase the switching frequency, that there is some losses related to the switching of the switching frequency, but also the inductor size as well. So, you might address that problem, but also you are introducing new problem by increasing the losses, which is going to contribute to reduce the energy efficiency. And also, that if you have got that higher voltage I mentioned, it can produce stress in the switch, and the voltage stress, current stress also you can find using that equation as well. Yeah, that's probably I already mentioned efficiency, size, cost, but other than that I already mentioned about the limitation and in voltage gain, even either step down or step down, but there is a inherent limit. And also when the boost converter is stepping up voltage may have limitation in the amount of voltage gain as well. So, not only stepping down, but also stepping up. EMI problem, if you have got high switching frequency, it can generate EMI, which is potentially affecting like other equipment in the system. And also proper PCB layout, filtering, shielding are often needed to mitigate that EMI problem. You can use like high voltage gain converter, but again that sometime very challenging to control, especially when you have got very fluctuating load, and sometimes complex topology might be needed if you want to achieve your desired gain and stability by having increasing design complexity. And as I said that it might have reverse recovery losses as well, but that can be addressed by using IGBT MOSFET instead of the diode. Now, that's like the conventional buck boost converter, but as I mentioned like that in previous cases. So, instead of diode, if you use like MOSFET, then you can reduce that problem of losses or reverse recovery problem of the diode, and that configuration or topology we call it synchronous DC to DC converter. So, the only difference is coming into that freewheeling diode, but other than that you see that everything is same. You can also use this technology to connect with the PV or even other renewable sources with the electrolyzer as well, but this one give like better efficiency compared to the previous one. So, yeah, so only difference, as I say, like we are using this low side MOSFET by replacing freewheeling diode, but other than that inductor capacitor doing the same purpose like storing and smoothing energy, reducing voltage ripple. But in previous cases you just control one switch, but here you are controlling both switches, but you have to make sure that you also address the date time management as well. So, you just need slightly bit better control, that's all. So, this one in terms of efficiency better, but in terms of control slightly I mean it's not that very complex, but comparing to previous one, complex control is required, and also that, as I said, like that dead time management is essential to prevent short circuit. But again, I mean this one is non isolated, so still you have got that isolation problem as well. So this is again, I mean just the comparison between these two. So efficiency, as I mentioned, this one will give little bit higher efficiency, lower conduction losses, and this one losses higher. So that means you need better thermal management. This one low losses mean less management you required. This one little bit better control, and also in terms of cost, because we are not using diode, so it would be slightly higher than the previous one. Next one, so this one is quadratic DC to DC converter. So as I mentioned previous cases, that in the previous one, the step up and step down, like proportional to the duty cycle, but here you can see that it actually quadratic, relation is quadratic. So the range could be higher compared to the previous one. So that's only the advantages, but what we are using instead of like that LC circuit. So to make it like quadratic, you need like multiple inductor and capacitor to have that quadratic relation between input and output. So that's the main difference. I mean if you compared with the previous cases, still here one switch, but here you have got more diodes compared to the previous cases. But here you can see that the relation is quadratic. So if you need like this sort of stepping up and stepping down, then probably you can use this type of topology as a DC to DC converter as well. So it could be like both fuel cell and electrolyzer, low voltage to high voltage DC application as well. So the operation I already mentioned, but it also like explained here as well. The third topology, that here that is stepping up and stepping down, doing stepping down, we are actually using a trapped inductor like in the primary and the secondary side. We've got like the trans ratio. So using this trans ratio, that also wants give you like to step up, step down depending on your requirement. So once we develop that duty cycle equation, it gonna be related with that trans ratio. So using that trans ratio, this one you can control the output voltage. So here you can see that relation between output and input, that is coming that trans ratio, which is again giving that by that equation. So sometimes people will also use this sort of topology. Again the main requirement, just like the requirement how much you want to step up or step down. If you need higher range, maybe that using this tapped inductor coil might help you to do that. So this one also thus I already talked about its operation. So this is probably one of the popular one, because this one actually can solve that problem. As I said, the ripple we might have in the output current, but if you use like that interleaved buck or boost converter, this one have got lower ripple current. So again it depends on how many leg you want. So for example, here example showing like 3, but you could have like more as well. So you could also find like 4th as well. So using this one depending on how many you have. So, you will have the control like the phase shift from each other. So, if it is 3, then definitely it going to have like 120 degree, but if you have got more, then I mean depending on you have the angle, and that can actually utilize to minimize the ripple current. And also once you have that better ripple current, you do not need very high volume that passive component as well. So, that is also like another benefit if you utilize I mean this sort of topology. So, yeah, I mean depending on like as I say like the voltage actually would be quite same, but main difference coming from like the current. So, here you can see that output current, sum of like current from like each phase. So, you are going to get like current that is coming and that is when you having the output current summation of all of this, that sometime the ripple current from like each phases that cancelling each other, that is how you will get the lower ripple in your output current. So, advantages I already mentioned one of them, reduce output, it will have better transient response, better thermal distribution among different component, high efficiency at high current, and also is scalable for different power level. As I say like it could be 3 leg, 4 leg, so it actually is scalable, and you need like compact passive component like inductor capacitor. But limitation again I mean it just like need better control, accurate current sharing control required, and again I mean this one does not have any isolation either. So, this one just showing like the voltage ratio with different duty cycle using different topology. I have not discussed all of them, but I discussed some of them. So, using that relation between input output, I mean if you just use different sort of duty cycle, I mean what sort of voltage you are going to get, that can be easily drawn if you just do simple experiment. Now, that was like non-isolated, but for isolation also we have got like different topology. Even in the market you will find different topology as well. So, the difference again I mean you need a transformer to make the isolation, but here I mean so if you have a like a PV, you could have DC to AC and then you have transformer AC to DC, this sort of combination can be utilized, and if you have DC you can yeah, that is quite similar things I already mentioned. So, the biggest advantage is that in terms of safety, because it is providing electrical isolation from input output, it also give like depending on the transformer ratio, trans ratio, allowing like significant step up or step down. You could have flexible grounding, input and output grounding can be independent. Isolation helps like better EMSC for lower noise, and also for essential grid connected high voltage hydrogen production system, also this sort of topology can be utilized. So, here also I mean you could have many different topology that is available in the market, and here I am just showing like some typical comparison like flywheel, forward, push pull, half bridge, full bridge, LLC, and it is giving their corresponding like power rating, but considering all of them, like currently as we need like higher power rating, probably that half bridge and full bridge. This would be like the one that in most of the cases people use half bridge and full bridge. So in terms of the power rating, probably that's the better one people are using. So I'm not going to explain all of them. I'm just showing like half bridge and full bridge, but other I mean it's quite widely available in the literature and also in different book as well. So if you are interested, you can have a look. But as this is mostly using, and if you are doing research, mostly you might be using one of them. So again, I mean half bridge and full bridge, you see that there is a power difference. So if you go full bridge, probably will give higher power. So it like increase, I mean in many cases now people are also going like high frequency transformer. So that's I mean very compact transformer available, and as I said, the galvanic isolation, high voltage ratio, it also might be given like soft switching operation as well. It has got different application, many of them I already mentioned. So it could be used like renewable to electrolyzer DC interface, high power electrolyzer system, which need like galvanic isolation. If you need like modular content hydrogen plant, backup isolated system, or EV hydrogen hybrid system as well. So for half bridge, you might know that I mean we use like 2 switch, and we use like 2 equal size capacitor. I am not showing like the DC voltage source, because you have got like half of them like as a input in both cases. So these 2 MOSFET like switch, and then again I mean when this switch is on and when this switch is on, depending on, you will get either positive V by 2 or negative V by 2. And when you have got positive, I mean one of these diode will be forward bias. In other cases, this one will be negative bias. And then in other cases, this one will be on, this one will be off. That's how you will get the complete path for the current to flow your load, right? And again, I mean this inductor capacitor, again I mean to reduce the voltage and current ripple. So again I mean you can think about like this capacitor voltage, is it DC or AC? Capacitor DC, right? But transformer we normally don't use DC, right? So here although you are saying DC, but at the end if you see the voltage coming across the transformer like this, so it is actually it's not sine wave, but it's still like a square wave. So it's like a square wave that gonna be coming. So as I mentioned, like depending on like which when that initial switch is open, I mean close, you're gonna get like a short circuit here, closed path, and then this diode will be like on, and one of them will be off. So again I mean depending on that you can easily have that corresponding equivalent circuit, and again by using that relationship between this, I mean you can easily have that the relation between input and output. As this is half bridge, you see like that voltage would be half, but other than that I mean operation is quite similar. And when you have got like the full bridge, how many switches you will have like the 4 switches, but other than that you have like transformer and then like rectifier, capacitor to get exactly whatever voltage you want. So, again this switch on and off that generate the alternating waveform as I shown in previous cases. And in the secondary, as you have got like this not DC. So, you need actually circuit exactly to make it DC, which is done by this secondary circuit and then filter exactly to find the DC voltage output. So, here this one output voltage you will get equation something like that. Again if you have that equivalent circuit, and from that actually you can derive this simple equation. So, again in terms of application, I think this is going like tens of kilowatt to megawatt. So, that is why this is one of the technology probably have got potential to utilize in the green hydrogen system. It also provide safety using the galvanic isolation, transformer and wide voltage conversion ratio. It possible like the soft switching, and it has got less voltage stress on switches compared to like half bridge at high power. So, that is all, but as I say like you also have many other topology, but few I already discussed. So, for your starting maybe you can start using them, and then also you can compare that whatever application you are comparing. If it is low power, then you might be not going for very expensive one, but if it is very high power, then maybe you go for the best one available in the market. Now, although as I say like many inverter topology are available, but still people are doing more research to find out what the best DC-DC converter for hydrogen system, focusing on even further improving the overall efficiency, reducing the cost, and not only the efficiency for the like electrolyzer, but also the overall system efficiency for large scale electrolyzer application as well. Not only like power circuit, but also people are working to have different control strategy as well. For having better performance from the DC-DC converter, because it's not only the hardware, but also the controller that also play a significant role, and other things people are also exploring, like that wide band gap semiconductor device like silicon carbide, gallium nitride, that can be used when you go for very high switching frequency, and also it has got high power capability as well. So, that is also like another research direction people are working as well. And the other one I say like that bidirectional DC to DC converter, mainly when you are using like the energy storage system. And as you see that when we trying to integrate the challenge of renewable energy, always we use like energy storage with the different technologies. So, in that case we need actually bidirectional DC to DC converter. And also like in most of the cases we have like initially say like let us say that you have got like 5 kilowatt system, right. Later you want to make it 10 kilowatt, 15, 20 and so more. So, you need like a modular design which can easily be like scalable. So, people now also doing research to find out modular and scalable DC-DC converter that can be easily adapted with different power level and also configuration for different level of growing hydrogen demand. And in that case also you need the fuel cell that variable capacity. In that case also you need the modular DC-DC converter as well. In terms of control strategy, although I mentioned, but that the model predictive control, this is one of them people now giving more focus. because this one actually can be utilized to optimize the operation of DC-DC converter. Yeah, there are many people now currently working in that aspect to solve the problem like voltage regulation, current ripple efficiency in like very dynamic operating condition. So, the other one is the adaptive control. People also working like doing adaptive control that can adjust the converter parameter and control strategy in real time to compensate for variation in the load voltage, load condition and component aging as well. So, the when you like use any component for longer period of time, it does have like deterioration in the capacity. So, if you have got the control that actually can adapt depending on the operating condition. So, that is also people currently working, and as usual another one is AI based control. So, again I mean AI now used in all cases, but also is using the DC to DC converter to optimize the performance of DC to DC converter when it is connected with the green hydrogen system. Wide bandwidth device I already mentioned this one. People are working to use that one to achieve higher switching frequency, and at the end when you have a higher switching frequency, that gonna give like a smaller, more efficient DC to DC converter. And as usual like the grid integration, I mean people trying to develop DC to DC converter that can seamlessly integrate with the grid, like enabling the use of renewable energy, green hydrogen production, potentially contributing to grid stability. Not only that, some other specific challenge that I mentioned, voltage or current stress for the different component. So, they are also trying that, finding solution to mitigate the high voltage and high current stress experienced by different component when you have got large scale hydrogen system. Electrolyzer characteristic, adapting DC to DC converter design to the specific characteristic of the different types of electrolyzer, ensuring like the optimal performance. And then as usual reliability and durability, people are also focusing on that as well, because the people always have like different inverter converter, but in many cases people do not think like how many years that switch can actually provide optimal design performance when you have got very wider variation in the temperature and so on. So, the power electronics reliability, now many people actually they are having project on the reliability on the power electronics as well. So, people definitely work the reliability in the electrical power system, but also that is getting like quite essential when you have DC to DC converter mainly in the very harsh operating condition. So, that is all probably I would like to share. So, so far I mean I believe now you have got good understanding about electrolyzer basic operation, different types of technology available in the market, like at least good understanding about their like performance, and in terms of application which one you might be going to pick up for a particular applications. And then we also talked about like there's few different types of converter that can be utilized, and yeah, finally we also mentioned like some research direction as well. Thank you. Thanks for your attention. Later when I am going to talking about the ancillary service provided by electrolyzer, I am going to show some case studies showing like grid application.
Okay, we'll
stability analysis. Is there any steady state model for this converter, or do we have
dynamics? Because when in like steady state, I mean we do not have any dynamics problem. So, steady state only use algebraic equation to model between input and output. So, steady state means that there is no variation in any signal, right. So, when we do like a load flow, right, we do consider steady state, because fixed operating condition. And dynamics comes when there is a change in the variable. So, yeah, to answer your question, yeah, we need dynamic model for studying stability. But if you just want to see like steady state voltage, then I mean you don't need the dynamic model, because you are not considering any changes in the system. But as I said that when we are going to talk about that ancillary applications, I am going to show some dynamic model to show how it is contributing to frequency ancillary service and also to regulate voltage as well. But I think that would be done even not tomorrow, day after tomorrow, right? Because tomorrow we are going to be talking about grid following, grid forming inverter. Thank you.